For inviting me to this. It's always a pleasure to come here. So as Ansh was saying, this will be very much a survey talk on proof complexity. So what I try and plan to do is to give you first a bit of a tour of proof systems, cover some of the main proof systems in the area, and then in the second part explain how this relates to and then in the second part of the talk, I say some relation to other areas of computational complexity, to some algorithms, which is receiving quite a bit of attention at the moment, to automatizability and also to first order logic. So let's start with the tour of proof systems, and maybe the best thing to start with is actually what is a proof system. So there's a very general framework for that. It goes back to Cook-Reckhow in the late 70s, and they were saying that a proof system now for a general language L is a function f that has as its range exactly this language L. Now what does it have to do with proofs? But if W is by f mapped to some x, which is from L, then we call this W an F proof for X in L. This may look rather abstract, but if you think of the proof systems that you are familiar with, it captures the two properties that we would usually expect. So correctness means that the range of F is contained in L, so everything that we prove here is in fact in the language. And the other inclusion is the completeness. So you will find a proof for all the elements in L. Now this by itself is not enough, because we should also be able to check the proofs efficiently. And this is captured by the requirement that this function is in polynomial times, computable in polynomial time. Now the main bulk of research in proof complexity has really studied propositional proofs, so you choose L as the language of propositional tautologies. And what kind of systems do we get? So let's look at the first but rather trivial example, truth table. For every formula you just give the complete truth table. Why is this not an interesting proof system? So most proofs are, or all proofs are actually of exponential size in that system. So what we try to do in proof complexity is we try to look for systems which have shorter proofs. And arguably the most studied and best understood proof system from a complexity point of view is resolution. So that even goes back to the 30s. That was introduced by Blake in his PhD thesis and later rediscovered by Davis and Boolean. It's a very simple system. You operate with clauses and you refute sets of clauses, so you refute C and Fs. What makes it compelling is that you have just one rule. If you have two clauses with complementary literals, so P in one clause, not P in the other one, you can derive C or D. And then the idea is you derive the empty clause, and by deriving the empty clause, you establish the falsity of the original formula. And there have been many subsystems like tree-like resolution, regular resolution, and lots more. And I think it's fair to say that we understand this system very well from the complexity point of view. So there are lots of lower bounds that we know. That's the main thing we care about in proof complexity. The most famous one is the pigeonhole principle. And actually that's also the first historical lower bound that we, the first exponential lower bound at least, that we have for resolution. So it's just the fact that n plus 1 pigeons cannot sit in n holes, and you can write that as a CNF by taking variables xij. Xij will indicate that the ith pigeon goes into the j's hole. So you have pigeons 1 to n plus 1 and holes from 1 to n. And then you have clauses saying that each pigeon sits in a hole. That's this type of clause. Then you have the small clauses which say whenever you pick two pigeons, they don't go into the same hole. And This, of course, is unsatisfiable, and Hagen, in an ingenious proof, actually showed this requires exponential size resolution refutations. So we have lots of other strong lower bounds for combinatorial principle mostly, like ordering principle, for graph theoretic principles, citing formulas, padding formulas, so on, and also for random 3CNFs, for instance. So for really huge class of formulas, we know that they are hard for resolution. So we understand resolution rather well, and because we have so many lower bounds, we conceive it as a weak system in proof complexity, because for many formulas the proofs are necessarily long. So let's in our tour jump immediately at the other side of the spectrum. What we consider a strong system, and that's a system that in proof complexity is usually called Frege system. You might also know it under the name of Hilbert system. That would be the more usual denomination if you look into a logic textbook. So what you have here is a set of axioms, simple tautologies, and then some rules. And usually what you do is you just restrict yourself to rules components. So from T1 and this implication you derive. That's a complete proof system. How do you prove things here? So in a Frege proof, that's a sequence of formulas. The last formula is the formula you want to prove, such that each such formula in the sequence is either a substitution instance of an axiom, so one of these formulas substituted for the variables, or it was derived by Rolle's exponents from previous formulas in this sequence. Right? And quite in contrast to the situation for resolution, that's a major open problem, and many people would say it's the major open problem in proof complexity to show non-trivial lower bounds for the size of Frege proofs. That is wide open. And what's even more dramatic, we don't have even candidate formulas that might be hard in this system. So a number of formulas have been introduced and suggested over the years, but eventually the story was always that they were claimed to be hard, and then someone later found a short proof for these formulas.
So the example, all the examples we gave for resolution are not short?
Yes, yes, they are all.
What is the size of a Frege proof? Does it also include the sizes of these formulas that are...
Exactly, yes, yes. So you just look at the binary representation of all the formulas and we add everything together. So you can also study different measure, you can also study the number of lines, so you can also take that as a measure, and that actually gives a different system. So typically you just count all the systems.
Candidate about perfection principles of alpha systems?
Yes, that's right. That's a candidate, and that we know that candidate would work. Sorry, I was simplifying a bit, but the trouble is we don't know how to analyze that. Right? Yeah. Yeah. So then there are lots of variations of Frege systems that you can study. You can weaken them a bit. Bounded depth Frege. In bounded depths, you allow only formulas of logical depth D. So you count the number of alternations of connectors, and if you have only formulas of logical depth D, then you can only prove these formulas, of course, but also the intermediate formulas in the system are required to be of that complexity, and that gives it a weaker system. And in contrast, for bounded depth Frege, we again have exponential lower bounds. Or fishbone principle, which is again. You can also make the system a bit stronger, so you can look at something which is called extended Frege, and here you can abbreviate formulas. So you can take up new propositional variables and just abbreviate any complex formulas you want. So in some sense, this is like working with circuits. You can imagine that Frege systems operate with formulas, whereas extended Frege systems operate with circuits, and that's also why people believe that this is really a stronger system. Alternatively, what you can do, you can allow arbitrary substitutions. That's called substitution Frege system. So whenever you have derived a formula, you can take an arbitrary substitution instance. So in Frege, you are not allowed to do that. You can just take substitution instances of axioms, but otherwise everything you derive, you would have to reprove it if you want to use it for a substitution. and then so that's known to be equivalent, EF and SF, they are of the same strength, so that's alternative views on it. And then you can, that's not even where it stops. What you can do is you can augment it by more axioms if you want. And it doesn't have to be finite, so you can take an infinite set of polynomial time computable tautologies and add it as axioms. And okay, so I was saying before several times that this system is stronger than this system, so what do we really mean by that? That is formalized by a notion of reduction. So there was
when you say polynomial time computable tautologies,
yes. What's
the input? What do you mean polynomial time and what?
In the formula. So they give you a formula and you say yes, that's an axiom.
Okay.
So when we want to compare systems, we need some notion of reduction, which for historical reasons is called simulation and proof complexity. And there are two notions of simulations. First one is the simulation. We say F simulates G. If whenever you have a G proof, then you can also find an F proof for the same formula, which is only polynomially longer, at most polynomially longer. So when F simulates G, that means whenever I have a short G proof, I also find a short F proof. Maybe not, the converse might not. And if I can do this transformation even efficiently, so that I can compute this W prime from W, then we speak of a piece coefficient. And like usual, we say that they are equivalent systems which they mutually simulate each other. So that's like a notion of reduction. Then we also have a notion of completeness, which is called optimality. So we say that the proof system F for language L is optimal or p-optimal if it simulates all the other systems. And what do we know about these strong systems? So first fact from Cook-Reckhow is that all Frege systems are polynomially equivalent. So it doesn't matter what kind of axioms you use and what kind of rules you use. So it's really a very robust definition. And it even doesn't matter what kind of logical language you use. As long as the Boolean connectives are complete, all the systems are equivalent in this respect to the size of then Frege Proofs showed that in fact any proof system is simulated by an extension of EF by further axioms. So I can take up a polynomial time computable set of axioms, an infinite set, add it to EF, and that will simulate my system. And these formulas are exactly the ones that Raoul was referring to. That's the reflection principle of the system I want to simulate. So that means with this construction I can build as strong systems as I want. Still, it's open, and we don't know very much about this, whether there exists an optimal proof system. So these systems can get as strong as you like, but we don't have any system that will simulate all the others.
You can't have systems for the other, Frege plus P, EF plus P. It is also true that every proof system is simulated by Frege plus some other.
Yes, yes, you can also have that, yes. Yeah, that doesn't matter so much what the base system is. The power really comes by the axioms. Okay, since this is a tour of proof systems, let me mention another one which probably most of you have seen before. So Sequent calculus, that's an alternative way how to prove things, goes back to Jensen from the 30s. Basic objects are sequence, so syntactically you denote it like this. You have a sequence here of formulas and here as well. And from these phi's you prove the size. You have initial sequence, that these are like axioms, they are two. And then you want to prove a formula, so you want to prove this sequence by the following rules. So we have a number of structural rules. You see weakening rules, exchange rules, because they are just sequences, so you need to syntactically manipulate them. Contraction, And then for all the logical connectives, you have some rules that manipulate them. And the important thing is you have a cut rule, which is a generalization of the resolution rule. In resolution, you can only cut over propositional variables, but here you can cut over arbitrary formulas. So, and what you can show is that this is in fact again equivalent to Frege systems. So Frege systems in the axiom plus rules formulation is equivalent to C2 brackets. So that's really a very robust system and interesting degree. And let me also say something about, a bit more formal about what we mean when we say this is a good proof system in terms of size. So the best scenario in some sense that we could hope for is that we have polynomial bounds on proofs. And then we call the system polynomially bounded. So this means there would exist a fixed polynomial such that every element in the language has an f proof of the size p of x. So all the elements in the language have short proofs. Let's look at an example. So if you pick the language of satisfiable formulas, then what would be a good proof system for that? Well, a standard proof system would be just to provide satisfying assignments, right? If I give you a formula phi, then a satisfying assignment for phi alpha can be interpreted as a proof for the satisfiability of phi, and otherwise you just output some satisfying formula. And this is obviously polynomially bounded, and obviously also the truth table system that I showed you in the first slide is not polynomially bounded. But what can we say about this in more general? So the interesting question is whether there is such a system for tout. Can we expect a polynomially bounded proof system for propositional tautologies? And it was a fundamental but really easy observation from Cook and Reckhow that this exists if and only if the language is an NP. So in some sense you can interpret proof systems as non-deterministic algorithms. So all the languages in NP have polynomially bounded proof systems and vice versa. And then of course for tout this means that you would have such a proof system exactly if NP is equal to coord P. And now this gave rise to something which is often referred to as Cook's program. So you could attempt to separate NP from coord P, and then of course also P from NP, by trying to establish superpolynomial lower bounds to the size of proofs in all propositional proof systems. Now, I mean, this may seem a bit elusive because how do you go about proving lower bounds for all proof systems? But okay, what does it really mean to do this? When you want to show a lower bound for a system P, it means you would have to find an infinite family, theta n, of propositional tautologies which are of polynomial size and require superpolynomial size proofs in the system. And actually what we usually target for proof complexity is not just superpolynomial but exponential size proofs. And usually what we can manage also is to actually construct these formulas efficiently. So it's not the principle, it would be enough to show that they exist, but usually you can even construct them in polynomial time, because how you get these formulas, where you take a formalization of some combinatorial principle. And it would be even better, like for instance with the CCNFs, to have a large set of formulas, not just one per length, but a large set of formulas for which you can show lower bounds. And now again, what do we know about this program? As I said before, it may seem elusive to actually do that for all systems, because we don't have a technique that is managing for arbitrary systems, but we have made quite good progress in the last decades for specific systems. So the first step I told you about was done by Arken, where he showed lower bound for resolution for pigeonhole. And the really major result was to push this for bounded depth Frege, that was done by Aitai, and then later improved by a number of people to exponential lower bounds. And we also have lots of lower bounds for other systems, like geometric or algebraic systems. And all of these lower bounds are actually exponential. And I think what's even more important, that in the course of this development, we found a number of techniques that you can employ to prove lower bounds for proof systems. So I think most notably there is the feasible interpolation technique, which transfers lower bounds from certain complexity into proof complexity. That was devised by Jan Frege, and that works for resolution, for instance, for cutting planes, for a number of other systems. Then there is an ingenious idea by Wenzel and Dickerson to actually prove size lower bounds by proving width lower bounds. So the width of a formula or width of a CNF is just the size of the largest clause in the formula, or in the proof respectively. Then there are quite a few game theoretic techniques, and I will show you later one of those in more detail. And a promising approach from the last few years is to use some cryptographic primitives, some what Frege was calling proof complexity generators. So we are trying to use a similar concept as pseudo-random number generators and try to come up with hard formulas and also for techniques to handling these formulas for strong systems. Nevertheless, all these systems, all these techniques currently are ineffective to prove lower bounds for strong systems. For this technique, for instance, we know that it will not work because feasible interpolation doesn't hold for Frege systems. There is hope that it could be done by game theoretic or by proof complexity generator techniques. That's a possibility, but we seem to be far from it. Maybe the last system in this tour is cutting planes. That uses the idea of linear programming. It's again a refutation system working with clauses, which you translate into linear inequalities. So the clause is translated into an inequality of this form, with integer coefficients, a's and b's. And propositional variables are identically represented by integer variables b. If you have the negation of p, that's translated into 1 minus p. And if you have a clause, then you just translate it into such an inequality that fi's are either the variables or 1 minus the variables, depending on the polarity. And then you just move the constants to the right-hand side and you get an equality of this form. And again, you translate all the clauses, you enforce that the values are 0 and 1 by these conditions, and then you have rules for manipulating these inequalities, addition, multiplication, and also division. And the goal is to refute the formula, so you're trying to prove an equality which is obviously false. Okay. Now it's an easy exercise that this system, I was rather hovering over the details here, but this system is simulating resolution. Converse doesn't hold, and Bird has shown that Frege systems actually simulate cutting planes. And we have separations between those. So here's a picture of the systems, of some of the systems that I've shown you so far. So this is the simulation order of proof systems as we know it today. You have to read it in this way that if I have a line between some two systems like this, then this system would simulate this one. And in fact, for all the systems below the dotted line, we have exponential lower bounds. So all of these are for sure not polynomially bounded. And moreover, all these systems are exponentially separated. But not vice versa. So let's just have a look what kind of systems appear here. So here you have the easiest one, truth table. Then you have here resolution, and I could also insert here lots of variations of resolution. Just I have tree-like resolution as an example. As I mentioned, this is simulated by bounded depth Frege and likewise by cutting planes, but they are incomparable. On the right-hand side, you have these algebraic systems that I didn't explain further. And all this is simulated by Frege. So these are the currently best systems that we know for which you have lower bounds, but all of them are simulated by Frege, extended Frege. And then you can take very strong logical theories, if you like, and try to use all the machinery that you have there to just prove positional tautologies. Still, somewhat surprisingly, you don't know whether even ZFC would be enough to form an optimal proof system. So this, I think, concludes the first part of my talk, and I wanted to tell you about some proof systems. So what I'm trying to say is that proof complexity is really at the intersection of logic and complexity, and uses concepts and ideas from many other areas to form proof systems. Main objective so far was to study length of proofs. And what I want to show you now is that this actually connects to many other areas. So we've talked about separation of complexity classes already. What I want to say next is something about sub-algorithms. So, I mean, you all know the problem SAT. You get a positional formula, you want to know if it's satisfiable. The traditional point of view is that this is a hard problem. Right? It's NP complete, so you don't have efficient algorithms, and much worse, most people believe that you actually need truly exponential time to solve the problem. So that's the traditional view, that SAT is hard. However, there is a sharply contrasting view from the SAT solving community, who tell us that actually, in their opinion, SAT is efficient. Right? So that relates to these SAT solvers, and they have been intensively investigated and improved since the late 90s. There's an annual SAT competition and a very lively annual SAT conference. And these solvers, they solve routinely industrial instances for model checking, verification, and so on, with 100,000, even millions of variables, which you wouldn't expect at all to be possible from a theoretical perspective, given these hardness results. That doesn't stop at SAT, because SAT is NP complete. You can encode many other problems into SAT, and that's what people are also doing. So you apply it to many areas, like, as I say, model checking, and, well, you name the area you want. So from a theoretical point of view, this really raises a few questions. The first one is, why are these SAT algorithms really so successful? And the second one is, maybe that's even more interesting from our perspective, what are their limitations? Okay, and one of the underlying ideas of SAT solving is most of the modern SAT solvers actually build on a very easy algorithm to find out whether a formula is satisfiable. So that's this DPLL procedure, going back to 60s, Davis, Putnam, Lokan, and Laughlin. I guess you've all seen that. You just choose a variable, you set it to a Boolean value, 0 or 1. That simplifies the formula, and then you do this recursively until you either find a satisfying assignment or the search fails. Right. So these SAT solvers, modern day SAT solvers, they are really based on this idea, but improved by a lot of other features. So they use unit propagation, clause learning, and restars, and I think clause learning was the main technique that actually made the breakthrough for these SAT solvers. And then there's also lots of implementation fine-tuning. So these SAT solvers really have been developed for more than decades now, more than a decade, and they are extremely fast for many industries. So, how does this relate to proof complexity? So, proof complexity gives you the main theoretical approach towards understanding how these subsolvers will perform, because if you just look at the very basic DPLL procedure, so the same DPLL procedure, it's well known that this corresponds to tree-like resolution refutations, in the sense that when I have an unsatisfiable formula, the DPLL procedure would implicitly generate a tree-like resolution proof of the formula. So what is tree-like resolution? It's again the resolution system where you operate with clauses, have this one rule, but then you also require that the proof is in form of a tree. So you are not able to reuse clauses that you have derived. You can only use every derived clause at most once. If you want to reuse it, you have to re-derive it. Okay, so the idea is now when you understand tree-like resolution, lower bounds for tree-like resolution will also give you lower bounds for DPLL procedures, and likewise for these sub-elements. So, and what I want to do now is to show you one technique that is effective for showing lower bounds for tree-like resolution. It will be a game theoretic technique, and illustrate how that would inform us about complexity of subsolving algorithms. So, an equivalent model to a tree-like resolution is actually Boolean decision trees. So what are these? These are binary trees where the inner nodes are labeled as variables from the formula, the leaves are labeled as clauses, and each path in the tree corresponds to a partial assignment, where you just follow the decisions that you make on the internal nodes on the tree and branch left according to whether you have 0 or 1. And the condition that you impose on this Boolean decision tree is that each tree, in each path that you follow in the tree, you must come to a clause which is falsified by the assignment. So you follow the assignment, you follow the steps that you do during the tree, and at the end you come to the leaf that's labeled with a clause, and that clause is false under the assignment. So what this does is it solves the search problem, which, given an assignment alpha, finds a clause that's falsified by alpha. And now it's not hard to see, it's a really easy exercise, that this is equivalent to a tree-like resolution in the sense that each tree-like resolution refutation of f would yield a Boolean decision tree for f and vice versa, where the size remains exactly the same. Right? So in what follows, you can now, instead of thinking about tree-like resolution refutations, you can equivalently look at Boolean decision trees. That's a more simple model. Right, so what I was saying before is on unsatisfiable formulas, DPLL will produce a Boolean decision tree. So that you actually can see directly from the description of the DPLL procedure that this holds. So that means you have a tree-like resolution refutation. And then to analyze the complexity of DPLL, all we need to do is to understand the complexity of tree-like resolution. Right? And let me try to show you how this can be done. So what I want to do now, maybe in the next few minutes, is to give you to explain a game theoretic idea how to prove tree-like resolution lower bounds. That works between two players. You have a delayer and a prover. So you start with an unsatisfiable formula, and the delayer is claiming that actually she knows a satisfying assignment. And then the prover challenges this and wants to find a contradiction by asking variables, one variable in a round, and the delayer then answers 0 or 1 and gets some points for his choice. So it's clear that in the end the prover can always win. worst case, he just deletes all the variables and then you know the result. But the question is, how many points can the layer earn in this process? So for how long can he consistently maintain this claim that he knows a satisfying assignment? Now, there are some details here. So when Proba is asking a variable x, what the delayer is really doing is he is assigning a probability distribution. So he is setting two variables, setting two weights p0 and p1 that sum up to 1. And when the delayer chooses a value b, either 0 or 1, the delayer gets some points which are actually corresponding to the information that the Proba is giving by his choice. So it's log of 1 over the probability. And if the Proba chooses the value b, which has probability 0, then the delayer effectively forces the choice because we say that the delayer gets infinitely many points if you choose that.
Sorry, is B is the value of x?
No, B is the probability. So this is the probability. The value is B. PB is B. So if you choose something that has probability 0, then so intuitively how you should think about this, the delayer is corresponding with the probability distribution, and then the Proba answers, and the best thing for the Proba actually would be to answer randomly with exactly the probabilities that the delayer is specifying here. Yes.
Previous slide you said as the delayer chooses the 0 or 1 value.
No, the Proba chooses the value. The delayer chooses the probability distribution.
Okay.
But the delayer, by doing this, the delayer can actually force some values for the Proba.
Can you go back one slide just for a second?
Sorry?
Can you go back one slide?
Yes.
We're confused because it says delayer and
Yeah,
says
the
0.
answer on the
Okay,
left.
this is in quotation marks. So the way you should think about this, the delayer can either answer the question directly. He can do that by setting the value 0 or 1 here. So a very unbalanced probability distribution. This way he would force a value and in some sense give the answer himself. Or he could defer the answer to the Proba. That would be the case when actually these both are non-zero, so it's a real probability distribution. And in this case, he would score some points according to the answer that the Proba is giving.
So all you're saying is that the delayer is allowed mixed strategies. That's
Exactly, yes, yes. Right. And now the intuition is that in each round, the Proba's point should relate to the amount of information provided by the Proba for a 0-1 choice. Right? So the Proba gives me some value and I charge him according to the information that this contains. And now what we can show is that for unsatisfiable formulas, the maximum score that you can achieve in this game, which we call the asymmetric Proba delayer game, is exactly St of f over 2, where Stf is the size of the shortest tree-like resolution refutation of f. So it's a characterization of tree-like resolution size in the sense that I can devise a delayer that is earning log of the minimal size of the minimal proof size many points, and also the other way around. So this gives me immediately a handle how I can show lower bounds for this system. What I can do is I can try to come up with a delayer strategy that gives p points to the delayer for f against any Proba. And if I can manage to find such a delayer that earns many points, then I know that all proofs must be large. Right? All proofs must be of f must be of size 2 to the p. Okay, and that's conceptually quite nice because in some sense you transform the task to show a possibility result, namely the non-existence of a proof, into a positive thing to come up with a delayer and show that this delayer scores many points. Actually, I see I'm running a bit short in time, so maybe I have to hurry up. But perhaps I can just explain how this works on an example. Let's take again the pigeonhole principle that I explained to you before. So you have these clauses saying that all pigeons go into a hole and there are no conflicts. And then what is known that this pigeonhole principle not only requires exponential size proofs, but in fact in tree-like resolution you would need proofs of size 2 to the n log n. So that means you have lower bounds of size n factorial. And that's actually a separation between tree-like and deck-like resolution, because in deck-like resolution you have exponential lower bounds.
So n plays no role in the size of the. So the n.
No, the m doesn't play over. It has to be bigger than n because otherwise it's not a contradiction, but otherwise it's independent of n. Now, how can we show such a result? So the original proofs were different, but with our technique, I mean, we can give a very easy and quite nice proof, I believe. So let alpha be a partial assignment to the variables that we have constructed so far in the game. So alpha is a partial assignment that we have built up to now. And let's look at this measure EI alpha. So you count the number of holes, maybe it's better to read this first. You count the number of holes which are still free, but explicitly excluded for pigeon alpha. So they are explicitly excluded because you have a 0 here for xij in your partial assignment. But they are also free in the sense that no other pigeon is sitting in there. Okay. And now the layer strategy works as follows. So if Proba is asking whether pigeon I sits in hole j in this game, the delayer forces a choice if he has to, because otherwise he would lose the game immediately. So if there is, so he chooses the value 0 if there is a pigeon that's already sitting in the hole, so if the hole is already occupied, or if in fact the pigeon I is already sitting in some hole. And also he is forcing a choice if he is worried about losing on pigeon I. So if this measure that we defined before, the number of holes which are excluded, is reaching a certain threshold, if it's going over n over 2. Because if many holes are already excluded for that pigeon, he could be worried that he's actually losing on that single pigeon by the prover keeping asking about that pigeon and not worrying about all the other pigeons. And then he assigns these probability distributions. And the intuition about this strategy is that the delayer will leave the choice to the prover as long as pigeon I doesn't already sit in a hole. The hole j is still free, and there are at most n over 2 excluded holes for pigeon I. Now, if you look at this probability distribution, the first thing you notice is the delayer will always earn more points when the prover is setting a variable to 1 instead of setting it to 0, right? Because you always earn log of the inverse of this, and the inverse of this is always bigger than this one. And this is intuitively correct, because when the prover is setting something to 1, it gives you lots of information. The 1 in this scenario implies lots of zeros, right? Because in that column, I can then immediately fill all the zeros. And in fact, you can explain this completely by an information theoretic interpretation. So when the prover sends a pigeon to a hole, the delayer should always get about log n points on that pigeon. Because you need exactly log n bits to specify in which hole the pigeon is going. Right? So, and therefore, the prover should be charged roughly that amount of points. And now you don't get the points at once, but there might be a process of getting to the points. But when we play the game, in each round, the delayer should always get some number of points proportional to the progress that the prover makes towards fixing pigeon I into a hole. So let's just look at an example. If we have a prover, if we have no information in the beginning, and we ask about xij, then the delayer should get the log endpoints immediately, and we fix the value to 1. And if you look at these probabilities, it's you get log over 1 over p1 points. So this is 0, obviously, so you get log n over 2. So roughly the log endpoints you want to have. If on the other hand you are already very far in the game, so you have n over 2 minus 1 holes already excluded, in the next round it will not matter anyway what in the next round the pigeon will be forced to hole anyway, so consequently you should get the same number of points, and if you see that ei minus 1 is this number and this is just 1, so you have 1 over 2 and 1 over 2 here, and it's an equal probability distribution, and you just score 1 point in each answer. Okay. So yeah, okay, there's an analysis that you have to do, but I think I'm skipping over that. So what in the end you find out that by the strategy you're ensuring that you end the game, or maybe we can go very quickly through. By the strategy you see that we end the game on the big on one of the big clauses. So you falsify one of the big clauses, and this can only happen by setting lots of zeros here. And by the layer strategy, this means that there must be lots of excluded holes for this pigeon on which we actually fail. And each of these excluded holes must come from other pigeons sitting in that hole. So in the end, what you find out easily is that at the end of the game, you have at least n over 2 variables set to 1. At least n over 2 pigeons sitting in holes. Then you can do an easy calculation that shows you that for each of the pigeons that are set to 1, we score log n points roughly. So you score this number of points for each pigeon, you score log over n over 2, and then you get these independently for all the pigeons, so you get in total the exponential overcount. Right? So I show you that the layer scores. Okay, so as I was saying before, this doesn't stop at, so this DPLL is in some sense just a very basic algorithm. So the modern sub solvers do quite a bit more. But even if you go beyond DPLL, you can interpret each run of a sub-algorithm on an unsatisfiable formula as a proof of unsatisfiability. And now the central task in sub-solving is to understand what is the corresponding proof system that is implicitly defined by the algorithm. So I give you an algorithm for SAT or for any other problem, and it will define implicitly a proof system. And what you want to understand is what is the power of these proof systems, especially for proof systems that come from modern SAT solvers, CDCL solvers. And I think it's fair to say that we have at the moment, I think we'll wrap up soon, at the moment we have a number of systems which have been put forward, but we don't understand exactly what is the right system for modern solvers. And it seems that they are tightly related to resolution, but it's not exactly clear if we get full resolution or strict fragment of it, or that's currently an area which receives quite a lot of research. So I was in fact planning to tell you some other stuff about automatizability and first order logic, but let me skip that completely and just mention very briefly that there are other aspects you can study in proof complexity. You can look at at this from a parameterized lens. So, and then this refines again the landscape that you see here, and actually proving lower bounds in this parameterized context will even become harder. because many classical formulas will become easy in this context. And let me also very briefly mention that, we talked so far about classical proof complexity, proving classical tautologies. But in the last decade, there have been many results actually on other logics. And so for non-classical logics, modal logics, intuitionistic logic, also for QDF. And that's quite interesting because most of these systems are more expressive. So you have more applications. And also we see different phenomena that you don't see in classical logic. And I just want to highlight some facts that in modal and intuitionistic logic, for instance, we have exponential lower bounds for very strong systems, namely for Frege systems. That's a quite strong result from Ugac and Dijabek a few years ago. And we also have strong lower bounds for sequence systems, for instance, for other logics, default logic, circumscription, and there's also quite a bit of interest at the moment on QBF proof systems, and actually that will be the content of the next talk. Leroy will tell you a bit of our latest work on QBF proof complexity, where again the idea is that you want to understand how proof complexity captures the performance of solvers, QBF solvers. So let me conclude. Proof complexity, the main object is to understand the complexity of theorem proving. There have been many strong results in the last decades in the form of exponential lower bounds. I think what's even more important, we know lots of very powerful techniques that have been developed to prove these lower bounds. And this relates to many other areas, into computational complexity, very importantly to subsolving, where this uncovers the algorithmic limitations that we have in this. Unfortunately, I wasn't able to tell you how this relates to first-order logic, but I think the general message you should take away from this is that proving lower bounds is quite hard, and the techniques we have developed here are sufficient for lead systems, but not yet sufficient for small systems. When you particularly look at this complexity, proof complexity sub-interaction, then what we want to do from the proof complexity point of view, we want to understand current algorithmic techniques and actually find simple and compelling proof systems that are coming from the solvers, and then we want to analyze their strengths. And I think the next talk will exactly exemplify this paradigm for QBF proof systems and QBF solving again. And from the sub-side, there is the question, well, why don't you use any of the stronger systems that we have developed? So, for instance, cut-and-plane polynomial calculus. And I think in general, there's a bit of a gap between these two communities at present, and I think there needs to be more interaction, and it's very timely development at the moment. I'm very excited. Thank you very much.
Questions? More questions?
So when you go from a SAT solver algorithm to a proof system, it's clear that the algorithm runtime translates to the size of the proof.
Yes.
But what other kind of relations are known between parameters of the algorithm and some parameters of the proof system?
Right. So that I actually had a slide on that as well, but I had to skip it. So one important thing is you can define something like a space of the proof, and that will correspond to the memory requirements of the solvers.
Also, space translates exactly as space.
Yes,
Okay.
yes. And I mean, people in the solver community actually argue that the main bottleneck for them is not running time, but what they see more often is that they run out of memory and have to give up the solving because the memory is out. And so in the last 10 years, there have been many results on trying to understand what can we say in terms of space, how space relates to time. So there have been trade-offs there have been exact lower bounds and trade-offs. They say that you can't optimize both things at the same time, so there will be formulas which have, for which you can optimize for space, but not for running time, but not at the same time.
Any other questions?
So earlier on you said that there are certain techniques, you mentioned that there are certain techniques, like the Krychek technique, the feasible interpolation for bringing circuit lower bound methods into proof complexity lower bound. But if one takes the analogy that bounded depth Frege is kind of analogous to AC0 in the circuit lower bound world, we actually have circuit lower bounds, the Razvarov-Smolensky lower bounds, which go slightly beyond AC0, namely AC0 with mod P gates, and there presumably is proof systems that are analogous to that, but for which I don't think there are lower bounds. So what breaks down in those methods that translate circuit lower bounds to proof complexity lower bounds that doesn't allow to get that does not allow an analog of the Razvarov-Smolensky results?
Yeah, that's a very good point that you mentioned. So the first thing I should mention here is that this analogy between the circuit complexity lower bound and the proof size lower bounds, that is something which is a bit of a vague concept. So in feasible interpolation, the lower bounds that you lift from proof complexity, from circuit complexity to proof complexity, are actually lower bounds that don't work on that don't mention the lower bounds that you the objects that you manipulate and the formulas. So for instance, for resolution, you use lower bounds for monotone Boolean circles. So you take the lower bound for the click color for the click color formulas, and for the click lower bound, so the monotone click lower bound, and translate that into lower bounds for resolution. But I mean, the objects in resolution are not monotone circles. And likewise, there's not really a transfer that would transfer the AC0 lower bounds to lower bounds for AC0 Frege systems.
But
we don't have that.
Isn't what I-type did somehow? Didn't I-type use some intuitions from what? Well, I don't know. Okay.
I think I-type's proof is really model theoretic, and there's I don't think that's building on these lower bounds. And you're absolutely right. The lower bounds for AC0 mod P, people have always thought that there must be a handle how to transfer that into lower bounds for AC0 mod P proof systems, Frege systems. But again, that's not known how it works. So it's a kind of vague analogy between the two things. Right? And likewise, I mean, in Frege systems, the underlying objects would be Boolean formulas, and that's not enough to give us proof complexity lower bounds. In fact, I think that will also feed into the next talk, because there Leo will tell you about the technique that we have used in QBF, where you transfer very directly AC0 lower bounds from circuit complexity into proof complexity. But again, it's not like this that you have to transfer on the same object. Like the proof system is modifying AC0 formulas in some sense, and is taking as input the lower bound. So there is a relation, but it's not as direct as you would like it to be.
Okay, I think we'll thank Olaf again.